Hey there, and welcome. From the super crisp audio in your favorite song to the sharp images on your screen, our digital lives are constantly being tuned and refined. But have you ever stopped to wonder how? Well, today we're pulling back the curtain on the invisible architects behind it all, digital filters.
Seriously, think about it. How do your headphones just magically erase the sound of a noisy bus? Or how does an app sharpen a blurry photo with one tap? The secret behind all that magic is a digital filter. They are the unsung heroes working behind the scenes in pretty much every piece of tech we use, silently shaping signals to give us the experiences we love.
So, to really get what's going on, let's start with the absolute basics. What exactly is a digital filter? I like to think of it as a really picky bouncer at an exclusive nightclub, but for data.
At its heart, a digital filter is just a process that takes a signal, say audio or image data, and gets rid of the parts you don't want. And just like that bouncer, it's got a list. It knows exactly which frequencies are on the VIP list and get to come in, and which ones have to stay outside. And this right here is what engineers are shooting for. They want to create what's called a passband. That's the blue area, where all the good stuff, the desirable frequencies, get through. Everything else, it gets tossed into the stop band, the red zone, and it's blocked. The real trick, the art of it all, is making that drop-off between the two as steep and as sharp as possible.
Okay, so that leads to the big question. How do you actually build one of these digital bouncers? Well, it turns out there are two main schools of thought, two completely different design philosophies for tackling the problem.
On one side, you've got FIR filters. This is the build-it-from-scratch approach, designing the filter from the ground up, purely in the digital world. And on the other side, you've got IIR filters, which take a totally different path. They find a brilliant, time-tested design from the old-school world of analog electronics and then cleverly adapt it for digital use.
So you might be asking, why would you bother adapting an old design? Why not just build something new? Well, it's because, as the source material says, the art of analog filter design is incredibly advanced. We're talking decades and decades of research. The IIR method is smart because it just leverages all of that history and hard-earned expertise. No need to reinvent the wheel, right?
All right, let's dive into that first philosophy, the FIR method, or as I like to call it, the build-from-scratch method. Think of this like getting a bespoke suit made. It is custom-tailored for one very specific job. The whole process really boils down to three main steps. First, you specify exactly what your perfect, ideal filter would look like. Step 2, you apply something called a windowing function, which is basically a clever mathematical trick to turn that impossible ideal into something you can actually build. And finally, you calculate the filter's core DNA. And this is what you get at the end of that calculation. Now don't worry about the math here. Just look at that last column, the one labeled h of n. Those numbers are called coefficients. They are the unique set of instructions, the magic numbers, that define everything about how our custom-built filter is going to work. And this is what you do with those magic numbers. They slot right into this final equation. And this equation, this is the filter. When a signal gets passed through this formula, all the unwanted frequencies are just stripped away, leaving only what you wanted in the first place. That's the FIR method in a nutshell. You specify, you window, and you build. Now let's switch gears and talk about the other school of thought, the IIR method. If FIR is like a custom suit, then IIR is like using the time-tested blueprints from a master architect to build a brand new skyscraper. You're starting with a classic, proven design that you already know works.
And when it comes to blueprints, there are some real famous ones to choose from. Names like Butterworth, Chebyshev, and Elliptic, they're basically legends in the engineering world. Each one has slightly different strengths and characteristics, but they are all well-understood, totally reliable foundations you can build on.
So let's just take the Butterworth blueprint as an example. This graph shows you how it behaves. See those different lines? As you increase a parameter they call the order, or n, that slope gets steeper and steeper. A steeper slope means the filter gets way better at telling the good frequencies from the bad ones. A higher order basically means you've got a much stricter bouncer at the door.
The most important thing here is that it's predictable. The source material uses this phrase, it decreases monotonically. Now, I know that sounds super technical, but all it really means is that it's smooth and predictable. There are no weird bumps or ripples in the response. When you use a Butterworth blueprint, you know exactly what you're going to get, every single time.
Okay, so you've picked out your classic analog blueprint, but now you've got a big problem.
How on earth do you take a design that was meant for physical things, like capacitors and resistors, and make it work in a world of just ones and zeros?
Yeah, this is the million-dollar question for the IIR method. You've got to find a bridge between these two completely different worlds. You need some way to translate the language of analog circuits into the language of digital code.
And this crazy-looking equation, this is the answer. This is the bridge. It's an incredibly powerful mathematical tool called the bilinear transformation. You basically feed the analog blueprint into one side of this equation, and poof, out the other side comes a perfectly translated digital filter ready to rock and roll. It's literally the Rosetta Stone for filter design.
So we have these two really powerful philosophies, building from scratch with FIR or adapting a classic with IIR. So why do we need both? Why not just pick one and call it a day?
Well, like so many things in engineering, it all comes down to trade-offs. You know, a little give and take. FIR filters, the custom-built ones, are great because they're always stable. They can also be designed to have what's called linear phase, which just means all the frequencies pass through at the same speed. That's absolutely critical for high-fidelity audio. The catch? They need a lot of processing power. IRR filters, on the other hand, are way more efficient, but they can sometimes mess with the phase, and if you design them poorly, they can even become unstable. At the end of the day, it's a classic engineering puzzle. Do you want precision or do you want efficiency? For your fancy noise-canceling headphones where audio quality is everything, you're probably going to find a precise, power-hungry FIR filter making sure everything sounds perfect. But for a quick photo sharpening effect on your phone, the lightning-fast efficiency of an IIR filter is the perfect tool for that job. It's all about picking the right tool. So, the next time you put on those headphones or slap a filter on a photo, just take a second to think about the invisible engineering that's at play. Is it a precise, custom-built bouncer, meticulously designed from scratch? Or is it a lightning-fast adaptation of a timeless classic, quietly shaping the digital signals all around you?